Okay, hi everyone. Well, I'm going to try and do something which is a little different from what I normally do for a living, which is I'm going to try and explain some math in a way that I hope will be interesting to younger folk. And I thought what I would do, I'm going to go through a few topics here, but they're all going to be about numbers today. Maybe another time I'll talk about geometry and shapes and things like that. Today I'm going to talk about numbers. And I'm going to go through several topics, but the first topic I want to talk about is how to make a very big number. So I have my trusty computer here, and I'm going to be able to type things in. So for example, one thing I might type in is say, what's 2 plus 2? And it should tell me the answer is 4. Okay, good start. So what the question we're going to be asking is, how can we get a really big number? Well, if we let's start off with something which is sort of an elementary thing to try. We say 2 plus 2 plus 2. Okay, what are we going to get? Everybody knows the answer to that. We get 6. We could say 2 plus 2 plus 2 plus 2. We're going to get 8. I'll try doing that. And yet another one of these. So first question is, how can we save ourselves a lot of typing here? What could we do instead of saying 2 plus 2 plus 2 5 times there? What's another way to say that? So I mean, we're repeating addition here, and another way we could say that is we could say 2 times 5, and we can write on the computer. We usually write a star for multiplication. We could, if we wanted to, we could make it do an ordinary times sign like that. But so 2 times 5 is a kind of short way to write out 2 plus 2 plus 2 plus 2 5 times. Makes sense? And so so this is kind of so like we could say, I don't know, if we say 3 plus 3 plus 3 plus 3 4 times, that's the same thing as writing 3 times 4. Yeah? So far so good? So by the way, I should explain for people who are on the live stream, I have a few sample kids here who are connected on a Zoom session more locally. And that's good because there's a bit of a delay in seeing the results from the live stream, and to get feedback is easier more directly. And possibly some of these folks will actually say things if we get some momentum going there. But okay, so everybody's so far so good? Yeah, maybe? I need feedback. Okay, yes. All right, so the first thing we're kind of learning here is that we can think of multiplication as being like repeated addition. Multiplication is just saying how many times we should do the addition. So this is saying we are adding 3 plus 3 plus 3 4 times. That's 3 times 4. Okay, next question. Let's say we say 2 times 2. Okay, that's 4. And we say 2 times 2 times 2. That's 8. Okay, so the question is, what happens if we, instead of, so before we said multiplication is what we get by repeating addition. So then the next question is, what do we get by repeating multiplication? So this is, now we can do multiply 2 4 times, and so we'll get 16. We can do the same thing 5 times. Kind of gets boring to type this. So there's a convenient notation in math that means repeat the multiplication some number of times. And that's taking a power, and we can write that for the computer as a wedge. So 2 wedge 5 means do multiplication 2 times 2 times 2 times 2 5 times. Okay, so we can work out, let's say we can do 2 wedge 2, 2 to the power 2. That would just be 2 times 2. We know that's 4, right? So, but here, so and often in math, power is written as a superscript like that. So we can say 2 to the power 3, which is the same as writing, so that's 8. That's the same as writing 2 wedge 3. 2 wedge 3 is just a convenient way to write it for the computer, okay? So this is, so what we're doing here, again, this is so 2 wedge 3 is the same as 2 times 2 times 2 3 times. Okay, so we could work out, like, let's say we could work this out. I don't know, 2 to the power 10. That's 1024. For people who work with computers, the powers of 2 are very famous because powers of 2 are a lot of things that work inside computers work according to powers of 2. So we can talk about that a little bit more later. Let's keep going with this. So let's say let's try doing. How about we try doing 2 to the power 100? Okay, so that's going to get us a bit of a bigger number. So remember what that is. That's 2 times 2 times 2 times 2, 100 times. Okay, but so the question we might ask, because this is kind of a typical kind of math thing to do, is this sort of generalization idea. So we got addition, we repeat addition, we get multiplication, we repeat multiplication, we get powers. So now the next question would be, what do we get when we repeat powers? Okay, so what does it mean to repeat powers? We'd say, okay, 2 to the power 2, that's 4. What's 2 to the power 2 to the power 2? Okay, that's going to get, for people who know a little bit more about math, there's a tricky thing about repeating powers. Okay, let me just show what happens when we repeat powers, and then we'll talk about the tricky thing. Okay, so this says do this powering operation repeatedly. So we're doing essentially 3 repetitions of this powering operation. Or we could do that 4 repetitions. We'll get a bigger number there. Or let's go to 5 repetitions of this. So this is saying we're doing this power operation all these 5 times. Okay, so then we get a really pretty huge number. So this is kind of I think the cheapest way to get a really, really big number is 2 to the 2 to the 2 to the 2 to the 2. So that's repeating. So each power is repeating multiplication. Each multiplication is repeating addition, and repeating powers is doing that sort of whole chain of things repeatedly. And this is a way to get, so we can get a really big number this way. And so, let's get a sense of how big that number is. Well, for example, let's see how many, let's see, we could say, let me just ask it. Let's do this. Let's say, for that number, let's just say, I'm just going to ask it, how many digits are there in that number? And it should tell us. Okay, there are 19,000 digits in that number. So one question we can ask when we get to these kinds of big numbers, we can get a sense of sort of how big is this. Maybe we should talk a little bit more about powers of numbers first. Okay, so let's talk about. Oh boy, that was a big number. Okay, we finally got to the end of that number. So okay, one type of powers of numbers that are really pretty familiar is powers of 10. So we have what's 10 squared, 10 times 10 is 100. 10 cubed would be 10 times 10 times 10, that's 1,000. How about, okay, who knows what 10 to the 6 is, for example? So that's 10 times 10 times 10, 6 times, and that is 1,000,000. We could actually ask it here, what is the name of 10 to the 6? And it should tell us it's 1,000,000. So like some of the powers of 10 have sort of famous names, like 10 to the 3 is 1,000. 10 to the 4 would be 10,000. People know what, so 10 to the 9 would be, if we do that, that's the number we get. We say, what's the name of that number? That's 1 billion. We could go, okay, how about even a bigger number? How about 10 to the 12? That's the next kind of famously named number. That one is 1 trillion. If we looked at, for example, if we look at 10 to the 10, that number doesn't have its own name, so to speak. It's just 10 billion. Okay. But so this is just looking. So remember what this is. This is 10 times 10 times 10 times 10, 10 times. That gives us the number that can be written out like that, and it's called 10 billion. Okay. And we had this way of getting to really big numbers, which is to repeat doing these powers. And just to give a sense of how difficult that gets, I showed you the thing we get by doing that 5 times here, and it was this big long number. Let's make the font smaller, then we can kind of see that number all in one gulp. There we go. Very small font. There's our number. Okay. So now the next version of this, the 6 times version of this, if we added another power of 2 here, I can tell you that basically we can't compute that number on any computer. So we can go, let's try asking what it is. I think it's just going to say blap, we don't know. Too big to work out on the computer. In fact, this is an example of something where sort of all the math we know right now doesn't even tell us what the first digit in that number is. We don't know if it's a 1, a 2, a 3, a 4, written out just as an ordinary number. So this is an example of how you can go from really pretty, you can go from something which is kind of like elementary math of just repeating addition with multiplication. Repeating multiplication gives powers. Repeating powers gives this operation. So this operation doesn't have a name that you'll hear in elementary math. Sometimes this operation is called power towers. It's called power towers because when you write out something, when you write out one of these powers, sometimes you'll write it out as a tower like that. Sometimes it's called power towers. Sometimes it's called tetration. It's called that because it's kind of the 4th in a series of operations, and tetra means 4. So that, but in any case, the thing that to me is kind of interesting is that it's so easy to go from things that are really elementary, like just adding numbers together, to something where sort of all the math we know right now doesn't tell us the answer, doesn't tell us, for example, the first digit in this number. Okay, well, so we can, let me show you a couple more things about things with numbers. Okay, so let me tell you an example of a kind of a theorem in math. So people, when one does math, a lot of what one's interested in doing is figuring out facts that are always true. So let me give you an example of a fact that's always true. So if I type in 3 plus 5, I'll get 8. If I type in 5 plus 3, I'll also get 8. So the fact that's always true is if you take a number and you add it to another number and you put that in a different order, you'll always get the same answer. So we can write that out in a kind of in symbols. We can say a number, we'll call it x here. We say x, that means 3 in this case, plus y, that means 5 in this case. Okay, so we say to the computer, what's x plus y? It'll just say, that's x plus y. I don't know what x and y are. I'm just going to leave them as x and y. But now, let's say we flip that around and we say y, and that our y was 5 here, plus x. What's that equal to? Okay, so the computer knows, actually, y plus s, it knows this math fact, this theorem about math. It knows that y plus x is always equal to x plus y. So it will just turn y plus x into x plus y. So this is an example of something that is true for any x and any y that we put in here. We can test this out with any number we want, and it's pretty easy to see why this is true. Just imagine that we make a number. I don't know. We could just make a number. Let's see. I think I have a conveniently made number here. Let me just do this. Let me just work out something here. I'm just going to use something just to show numbers in a form that's easy to see. Okay, so this is a number. So here's just a way of writing out the number 4. We just got 4 dots. Let's say we want to write out the number 5. We've got 5 dots. Okay, so how do we know that 5 plus 4 is the same as 4 plus 5? Well, we could write that out see if I can write this out here. I wonder what's going to happen if I try doing this. I think I might be able to just write that out. Okay, there we go. So we see that 4 dots plus 5 dots. Okay, so it's pretty obvious that we can move these dots around. Doesn't matter where these dots are. The answer for how many dots are there altogether is going to be 9 dots. It doesn't matter whether the dot is on, whether we put these dots on this side or on this side. And so that's kind of a proof that whenever, if that collection of dots is called X, the next collection of dots is called Y, that's the same thing. X plus Y is the same thing as Y plus X. So maybe we can do this with 3 numbers. We can say we have a number X, a number Y, a number Z. We could say, what's Z plus Y plus X, for example? And the computer will then tell us, well, actually, that's the same as X plus Y plus Z. And what the computer is just for convenience. It's showing us, if we say Y plus X, it's showing us its kind of standard form for what the answer is. Because that means that if we say what's Y plus X, I mean, let's say we say, okay, let's do something a little trickier. All right, let's try something a little trickier. Let's say what's X plus X plus X. Okay, so we've got 3 numbers. Let's say the number is 2. We got 2 plus 2 plus 2. That's 2 plus 2 plus 2 is otherwise known as 2 times 3, which is okay, so let's see what the computer does for that. So X plus X, it says, is 3 times X. So here's the next interesting fact. Okay, so various people are asking, why does the computer decide to make Y plus X equal to X plus Y? So what it's doing is it's trying to put things in a standard form. So it's trying to make sure that however you type in something which is equal to X plus Y, it will always actually write it as X plus Y. The actual method it's using to decide that this should be X plus Y rather than Y plus X, it's just putting these things essentially in alphabetical order. So for example, if we had, I don't know, let's say C plus S plus A, it'd probably put that as A plus C plus S. It doesn't really matter in the end what order it puts it in. It's but it's just its convention is to always put the things in alphabetical order. Now, if we put in something weird here, I don't know, we put a let's put in some kind of happy smiley plus a sad smiley. I have no idea what order it's going to put those in. Okay, it decides happy comes before sad. But the main point is that whatever we do, whatever order we put these in, and let's put the sad smiley in first here. Whatever order we put them in, it'll always give the same answer. It'll always decide to put the happy one before the sad one. And that's convenient because if we want to know, if we're working things out in several different ways, it's really convenient for the computer to always make everything that is equal look the same. So, okay, so let's try looking at so our first kind of math theorem is the theorem that X plus Y is the same as Y plus X. Actually, we can just ask the computer, is X plus Y, and that thing means test whether these are the same as Y plus X. And it'll say, yeah, it's true. X plus Y is the same as Y plus X. If we said, is X plus X the same as X plus X plus X, it'll say, oh, it doesn't, yeah, okay, let me do a simpler thing. Let's just ask it, is 4 the same as 4? Okay, it'll say, yeah, 4 is the same as 4. Is 5 the same as 7? No, 5 is not the same as 7. Okay, the slightly trickier thing that was happening in what I just did was I say, is X the same as 5? And it says, I don't know, because it depends what you mean by X. It doesn't know whether X it says X could be 5, in which case this is true, or X might be 7, in which case this isn't true. So we could ask it, I don't know, is well, okay, here's the thing we can go to. I don't know, it might be too advanced, but we'll see. What we're doing is kind of a version of algebra here. Whenever we're using a letter to represent, for example, a number, that's kind of the idea of algebra. it's actually remarkable how long it took people back in the history of mathematics to invent algebra. It wasn't invented until the 1400s, which is kind of late in the, because arithmetic was invented. Lots of things about arithmetic were known 4,000 years ago and so on. But algebra wasn't invented until about 600 years ago. But in any case, so the kind of thing that happens in algebra is we can say things like, if x plus x is equal to 10, then the computer will say, okay, that's the same as 2 times x being equal to 10. And what we can do is we can say, okay, if 2 times x is equal to 10, what is x? And we can figure that out. We can ask the computer to work that out by saying, solve for x in here, and it'll tell us if 2 times x is equal to 10, then x is equal to 5. Okay? Okay. So I was going to show you one more kind of math theorem fact that you probably already know, which is that x times y is the same as y times x. Okay, and that's we can I mean, let's just do some examples. We say 5 times 3, it's 15. We say 3 times 5, it's 15 as well. We can kind of see why this is true, because we can say, let's take 3 and we'll repeat it 5 times here, or let's take 5 and we will repeat it 3 times. And we should get the same answer in these two cases. Well, let's see. I'm not getting as much feedback as I would like, because I'm not knowing whether I can try and show you why this will always be true, that x times y is the same as y times x. But let's maybe move on, because you might say, well, does that mean that anything? These are both operations we can do, addition and multiplication. So here's an operation. They can be done in any order. The math name for that is that they're commutative. The computer name we tend to use is that they're orderless. Same thing, commutative, orderless, same idea. It means that you can do the operation, you can put in the inputs in any order. You can say 2 plus 6, you can say 6 plus 2, you'll get the same answer. Okay, so can we think of an example of an operation that isn't commutative, that you all know about? It's okay, so yes, powers are not commutative. That is a good example. I was going to do an even more elementary example, which is subtraction. So 6 minus 3 is not the same as 3 minus 6. So it's just an example of an operation that doesn't have this property that you put things in the opposite order and you'll get the same answer. So another thing that doesn't have that property is powers. 2 to the power 3 is not the same as 3 to the power 2. Why is that true? What is the fundamental reason that's true? That's a good question, actually. Well, let's see. To know why it isn't true, maybe we have to know why it is true, for example, for multiplication. We could see why it was true for addition. That was really easy. For multiplication, let's see, what's the best way to figure out why it is true for... why is this true? What's the best way to show why this is true for multiplication? I think what we want to do is to say, yeah, I mean, we can do it by sort of repeating what we did for addition. The reason that, generally, there's no reason for things to have this property that you can do them in any order. It's only very special operations for which this is true. Okay, so a question on the live stream, is it true for any x and y that y to the x is the same as x to the y? Okay, so that's a really tricky, complicated equation. Let's see whether the computer can find an answer to this. Let's see. I don't know whether it can. Let's just see what it can do. I think it's having a hard time finding the answer. Okay, let's just try one more thing it might be able to do. Computer can't find the answer. However, we can be a little smarter, and there is in fact one answer to that. So in fact, 2 to the 4 is 16, is the same as 4 to the 2. And that's the unique answer. If we want to work out if we say x to the y, it's an equation, x to the y is the same as y to the x. That's true in only one case. It's only true for x and y being 2 and 4. So it's a bizarre fact. It's not true for any other. Actually, we could figure out. Okay, let's. I'm getting dragged off into a slightly more complicated discussion here, which maybe I shouldn't do. But just to give a sense of how we would figure this out, let's try doing this. Let us try. Let's try negative numbers as well. Now let's go to 4, for example, here. Just to give a sense of how we might. Oh wow, that's complicated. Very complicated and very messy to understand. Let's just see here. How can we show this? Well, yeah, sorry, this is really hard to understand. This is, I'm making a plot of these two functions, and the place where they'll be equal is the place where they cross over, but it's pretty hard to see that because these things are increasing. Oh, I see it. That doesn't help. Let me do this. I messed something up here. Okay. Oh, that's cool. All right. So what's a little hard to understand what's going on here, but the place where there's that result, where x to the y is equal to y to the x, is right at that point there. Okay, Simon on our live stream is suggesting that I can prove the result about multiplication and addition. Let's see whether this is right, by saying make a, let's see what happens here. Let's see. Oh yes, this is a good idea. Yeah, thank you. Thank you. Okay, so what I'm going to show here, this is an attempt to show why 4 times 3 is the same as 3 times 4. And actually, this is going to get us into another really interesting thing. Okay, so this is a representation of 4, let's say 4 times 3. Right? We got 4s, you know, a 4 here, a 4 here, a 4 here. That's 4 times 3. But actually, we could just say, let's represent things the other way around. And let's say this is 3 times, let's say, sorry, we said this is 3 times 4. We've got a 4 there, a 4 there, a 4 there. We get the result, it's 12. But we could also say, let's take this the other way around. Let's say we've got 4 copies of 3. We've got a 3 there, and we say 3 plus 3 plus 3, 4 times, and we'll get the same result. We could as well have flipped this around and drawn our picture differently. That's terrific. Thank you. So there's a question here. Okay, there's questions about, is there any way to make powers or subtraction commutative? I don't think so. I don't think so. There is, yeah, I don't think there's a way to write those out so that yeah, okay, and somebody is pointing out, okay, something that I said that was a bit silly was if this question of y to the x and x to the y, if x and y were the same, this will always be the same. Like if I'm typing 3 to the 3 and the 3 is x, the 3 is y, or the 3 is y, the 3 is x. Yes, this will always be true when x and y are the same, but that's kind of obviously true. The only case that isn't obvious is the case where that's yeah. So okay, so this question about actually a comment on the live stream here, a way to make minus Okay, yeah. A way to make minus commutative would be to use this thing called absolute value. And so what is the absolute value? So absolute value is saying, let's say we have 6 minus 8. We say, what's the difference between 6 and 8? Well, the difference, they're two apart. If we think about 6 and 8 on like a number line, they're two apart. It happens that 6 minus 8 is minus 2. 8 minus 6 is, 8 minus 6 is 2, but they're still always two apart. And so one way we can represent that is with this thing called abs. So abs says give us the absolute value. So absolute value just means what's the number that's there without saying whether it's positive or negative. So we can, if we say what's the absolute value of minus 9, it'll be 9. What's the absolute value of 9? It'll be 9 as well. We can ask things like, what's the absolute value of 0? That'll just be 0. And we could, for example, let's make a plot of absolute value as a function of x from minus 5 to 5. And then, so what will that look like? That will look like this. That's saying for all the positive numbers, like 2, for example, the value of the absolute value of 2 is just 2. For the negative numbers, the value of the absolute value of minus 2 is also 2. So that's what the plot looks like. And so this is so yes, it is true that we can make, if we decide that we're going to take, if we decide we're going to use absolute value whenever we do our subtraction, then, so we're going to make a sort of absolute value subtraction, then that will be commutative again. So we can say, because it's really saying how far apart are these numbers, rather than what is the result of the subtraction. It's just how far apart are the numbers, and that's something where it doesn't matter which order we put the numbers in. Like we can say, I don't know, we can probably say number line plot. We could say something like 6 and 8, put that on a number line plot. Okay, we might want to show, okay, so there's our number line plot. Let's say plot range from 0 to 10, for example. Okay, so there's 6 and 8 on our number line. We can say, how far apart are these? Well, they're two apart. If we say, what's the subtraction? 6 minus 8 will get minus 2. But if we just ask what's the distance apart, it's just 2. Okay, so actually what Simon on our live stream was commenting on makes me want to talk about something else, which is I want to talk about if we have a number that let's say we have a number and we make the number up as 5 times 7. Okay, we take 5 times 7. 5 times 7 is 35. There's a question of if we wanted to figure out what can we make 35 out of, how would we do that? So we want to work out, we just worked out 5 times 7 is 35. The question is, can we go the other way around? Can we say, what is 35 made of by multiplying numbers? Okay, so in a sense, what we're doing here, if we look at this in terms of the, in terms of something like this, here, that's a good way to do it. We could say here, we could sort of make up 35 by saying it's 5 times 7 here. And we could make that up by showing, okay, it's this rectangle of dots, and there are 35 dots altogether. There's 5 dots across the top, 7 dots going down. Total number of dots is 35. Okay? So question is, well, first question is, what numbers can we make up as numbers of dots in rectangles like this? So in other words, what numbers is it true that, for example, if we say 4 times 8, that's 32, okay. It's pretty easy to go from numbers, multiply them together, see what we get out. Question is, how do we go backwards? How do we know, if I give you the number 31, for example, is there a rectangle of dots that makes the number 31? Let's take a simpler example. Let's take the number 6, okay? So we can pretty easily figure out, so what would be the rectangle that makes 6? So that would be this we can do that by just saying 6 we know is 3 times 2, so we can make a rectangle here that shows 6. Okay, so 6 is 3 times 2. We know how to break down 6 into multiplying two numbers together. All right. Okay, what happens if we try and do this? What about 8? Okay, so if we do 8, what's 8 equal to? Sorry, unary number. Yeah, I defined unary number somewhere else. Sorry, I didn't. Let me write down the definition of unary number form. I was just making this as a way to sorry, this requires a little bit of code because it's not set up. Let's do it as like this. We can say row of table of one of these bullet things, which you can type in as escape BU, and then we say n here, and that we should. Let's just check this still works so I didn't mess it up. Let's see, this should give us, oh, those are smaller. Oh, let me do it a different way. Sorry. Let me do this a different way. I think I was making little discs there. Let's check that that works. No, that was too big. All right, let's now this is the let's make tiny discs. Let's see whether that works. That didn't work either. So let's make all right, let me cheat and look at how I defined this before. All right, I have a way to do that here. All right, I'm gonna just use this definition. Okay, and that was a okay, with that definition, this should work again. Yes, it does work again. Okay, so somebody is commenting here about okay, so let's do this for 8 again. We're going to try and make up, so how can I make up 8 as a rectangle? What so one way I can make up 8 is 4 times 2. So let's do that as a rectangle. We can actually, let's write a function here. Let's call it rectangle form. And we can just write that as, and we'll give it 2 numbers here, let's say m and n. And we'll write that as here, just an m and an n. So I'm just telling the computer how to do this. And I could say, show me the rectangle form that makes 8. So there it is. Okay, so there's another way to make 8. What's another way to make 8? We could make it as 2 times 4, 4 times 2. We could also make it as 2 times 2 times 2. But let's just think about it as in terms of pairs of numbers. Well, let's try making. How about we make 12? Okay, what's a way to make 12? So we can make 12 as 2 times 6. Okay, we can also make 12 as 3 times 4. So both of those, so let's make those in terms of rectangles. 12 is 2 times 6. We can make the rectangle for it, there it is. It's also, it could be 6 times 2. We can also make it as 3 times 4. Okay. Okay, so here's the big question. The big question is it true that all numbers can be made as rectangles like this? Maybe we start off with a simpler question. Okay, let's see. There are some numbers where we can make them as squares. So, for example, if we say 4, well, let's say 3, 3 here, that will be a number that we can make up just with a square of dots, and so that's it's 3 times 3. So any number that is like 3 times 3 is we can make as a square of dots. So these are the numbers that are usually called the squares because we can make them with squares of dots. And so, for example, 3 times 3 is 9, 4 times 4 is 16. We can make, there's a whole series of numbers which can be made as squares. We can make a whole table. Let's make a table of the first 20 squares. So those are all the numbers, 1, 4, 9, 16, 25. Each of those numbers can be made as a square of dots, okay? And we saw that some numbers, so the only numbers that can be made as squares of dots are these numbers here, right? So for example, the number 25, well, the number 36, for example, would be the the 6 by 6 square of dots, and so on. Okay, so question is, can all numbers be made as squares of dots? Okay, so the answer is going to be as rectangles of dots. So there's a really boring way we can make any number out of a rectangle of dots, which is we can just say it's a something by one rectangle. Okay, so for example, 7 we can just make as a rectangle of dots that way, but it's a very boring rectangle. So the question is, can we make a not completely boring rectangle of dots using the number 7? Okay, so maybe you can try and actually figure it out on a piece of paper, I can tell you the answer. The answer is you can't make a rectangle other than this trivial rectangle out of 7 dots. And the sort of the math way of saying that is that 7 is a prime number. 7 is a number that can't be written as a product, as a multiplication of other numbers. So we could work out, so if let's try starting with the first few numbers. So let's say, let's try 4. So 4 we can clearly write as 2 times 2. It's not a prime number. Okay, how about 5? So can we write 5 as a multiplication of other numbers? Well, what are the choices of numbers? We could say, is it 2 times 2? No, it isn't 2 times 2. Is it 2 times 3? That's the next possible multiplication. Well, it's not that either. And actually, we already got, so that means there isn't any number we can use to make 5, because it would have to be something in between 2 times 2 and 2 times 3, and there aren't any numbers in between there. So that means that it has to be the case that the number that we get, that 5 can't be made by multiplying numbers together. Okay, so we can ask the question, what numbers have this property that we can't make them by multiplying other numbers together? So for example, 6, well, we know 6 we can make by multiplying numbers together. 7 is another number we can't make by multiplying numbers together. And we can start asking, what are all the numbers that we can't make by multiplying numbers together? So we can ask, this is a thing that just tests whether a number is prime. So whether a number can be made by multiplying numbers together. So 10, for example, no, it's not a prime. It's 2 times 5. For example, 11, that is a prime. There's no way to break down 11. There's no way to make a rectangle of dots where there are 11 dots and it's not a trivial rectangle. So we can start figuring out, let's see what I can do this from, let's see if I can pick this up here. I'm trying to figure out on my screen how I pick something up here. Okay, there we go. Somebody conveniently sent me a piece of code, which I'm going to dangerously just run on my computer. Okay. All right. Well, this is what this piece of code does, is it highlights all the numbers that are prime. So between 1 and 100, it's showing us which are the prime numbers. So it's showing us 2 is a prime number. It's kind of a weird prime number, but 3 is a prime number, 5 is a prime number. So notice, for example, that the numbers which are squares, like 9, that's definitely not a prime number because we can make it as 3 times 3. 10 isn't a prime number, and so on. So we see these prime numbers are kind of dotted around. Okay. Now, if we can work out, for example, we can systematically, we can try and figure out, how do we work out which numbers are prime? How do we make this pattern of primes? We could try to figure out, let's make this for a much bigger case. Let's do, for example, let's say what's the pattern of prime numbers? Let's see what this looks like. Let me live a little bit dangerously. Let's see how to do this. Well, let's just go to at least 900 here and 30 there. Okay, and let's make this a bit smaller. Oh, that's kind of interesting, actually. So this is showing. So I'm writing out the numbers from 1 to 30. Well, 1 to 900, and I'm showing here all of the numbers that are prime. And okay, actually, it's kind of interesting. I'm a little surprised here that there are so many patterns in this picture. Let's see whether we can figure out why there are patterns in this picture. Okay, so I can start to see some answers to why there are patterns in this picture. So one question is, can a number that ends in a 2 be a prime number? So that's any number that ends in a 2 must be an even number. So for example, 32, it's an even number. If we just write out a table of even numbers, we'll find the numbers, okay, numbers that end in 2, 1, 2, 2, 2, 3, 2, and so on, they're always even numbers. That means even number means we can divide it by 2 and we'll get a whole number. So if we're trying to figure out what numbers can possibly be prime, we can already say immediately any number, an even number, clearly isn't prime, because we can make it like a number like, let's say, an even number like 14. We can always say divide it by 2, we'll get 7. So we can always make 14 out of 2 times 7. Makes sense? So we know that numbers that are even can't be prime, and numbers that end in 2 are even, and therefore they can't be prime. And so here, when we look at this pattern here, these are all the numbers that end in a 2, and none of those numbers can be prime. Same thing for numbers that end in a 4, they can't be prime. Numbers that end in a 6, they can't be prime. So we're already a bit constrained in this pattern. Numbers that end in a 1 can be prime, numbers that end in a 7 can be prime, some numbers that end in a 3 can be prime, some numbers that end in a 9 can be prime. Okay, if you're thinking about a little bit more advanced math, you can understand why a bunch of these numbers that end in 3s can't be prime, because there's a rule that says if the digits of a number add up to a multiple of 3, then the number has to be divisible by 3. Okay, so somebody is asking, can we visualize a graph of what numbers are prime? Okay, well, there's an easy way to do that. We can say, so for example, one thing we might ask is, okay, so let's try and show what numbers are prime. So we can just ask, what is, so we've seen, if we look at numbers, let's say from 1 to 10, this has shown us, let's just do this again. This shows us, let's just go numbers from, let's say, okay, numbers up to 30. This is showing us, highlighted in red, which numbers are prime. Okay, and so we can say there's a thing where we just ask, what is the first prime? It's going to tell us, okay, the first prime is 2. What is the second prime? Okay, the second prime is 3. What's the third prime? Third prime, we can read it off from here, is 5. The fourth prime is 7. Okay, and so what we can do here is we can make a table of a bunch of primes. So let's say we make a table of the first 100 primes. So this is going to show us 2, 3, 5, 7, 11, 13, etc., etc., etc. So we can ask the question. This is kind of showing us which numbers are prime. So for example, one thing we could do is we could say, make a plot that shows us how big is the nth prime number. So we can say how big, so we can take that list of numbers and we can say, make a plot. So what this is showing, let me do it for a smaller number here. What this is showing is, this is showing the first prime number is 2. The second prime number here is 3. The third prime number here, we'd have to read off here, should be 5, and so on. Okay, so this is a plot that shows us for the sort of the serial number of the prime, how big is the prime? Okay, so serial number of prime is 10. The 10th prime, well, let's work out what it is because I don't know what it is 29. Okay. Okay, so we can ask the question, if we extend this a long way, let's see what this looks like for 1,000 primes. Okay, that's what it looks like. It's kind of almost a straight line, except you can see it has little wiggles in it, except that we see that the 1,000th prime is about 8,000. So what does that tell us? That tells us that if we were to ask, it tells us that when we go 1,000 primes out, that will be 8,000. So it means that the fraction of numbers that are prime is about 1 in 8, at least when we get out to 1,000. So we can ask these questions like, so you're asked to sort of plot the prime numbers. This is a way to plot the prime numbers. Another thing we could do is to say what are the differences between prime numbers. So we can let's take these numbers here, the first 100 primes. We could say how far apart are those primes. So these primes are 1 unit apart. These are 2 apart, 2 apart. Now this is where my arithmetic has to be challenged. Those are 4 apart, 2 apart, 4 apart, and so on. So we can work out, can say differences, and that's going to tell us the differences between these primes. So that's going to tell us the 2 and 3 that was 1 apart, 2 apart, and so on. So this is showing us how far apart the primes are. So this is saying this is saying here there are some primes which are 10 apart. Here there are primes that are 12 apart, and so on. Okay, so sometimes there are primes that are 2 apart. So the first, for example, 3 and 5 are primes that are 2 apart. 11 and 13 are primes that are 2 apart. Okay, so let me tell you a math fact that sort of an interest. Okay, first math fact is, so one question is, are there an infinite number of prime numbers? In other words, if we just keep going, will we always find it to be the case that that we can make bigger and bigger and bigger rectangle? We can make numbers that are bigger and bigger that can't be made into rectangles. Could there ever be a biggest prime? Could there ever be a number where it's just like every number above that number, we can write it as as a rectangle. We can write that number as a product of 2 other numbers. Okay, so a math fact is there are an infinite number of primes. In other words, it never stops. You can always get a bigger prime number. So we could say, what's the millionth prime? Okay, that's a fairly big number. We could say, what's the billionth prime? I think we can still work that out. Okay, there it is. I think it's going to get really difficult here. Maybe we can do the 10 billionth prime. Okay, so that's to know what is the billionth prime. That's a hard thing to know. But in any case, it's a math fact. Even though it's hard to work out those big primes, it's a math fact that there are an infinite number of primes. Now, I think, how do we know that? It's a little tricky. We probably could, with a little bit of effort, I could probably manage to explain to you why it's true. Just a history fact, the fact that there are an infinite number of primes was proved, was by a guy called Euclid, who also worked a lot on geometry, and that was in around, I think, 2nd century BC. So we've known for about 2,000 years that there are an infinite number of primes, and it's an interesting math fact. It's a math fact we can't. Okay, so now if we look here, we can ask these differences between primes. We've noticed that there are some primes which are just 2 apart. Those are called twin primes. So for example, 11 and 13 are twin primes, okay? Primes that are just two apart. Okay, so here's another math fact. You might ask the question, are there an infinite number of twin primes? Are there an infinite number of pairs of primes just 2 apart? Okay, so there, it's maybe a bit of a disappointment. The answer is nobody knows. That's been a problem that people have wondered about in math for about 2,000 years, and we still don't know the answer for whether there are an infinite number of twin primes. Actually, there have been results just in the last few months that may suggest that may suggest a proof that there are an infinite number of twin primes, but we still don't know. After 2,000 years of trying to figure things out in math, that's still something we don't know the answer to. And so it's sort of interesting that there are these questions in math that go from the really quite easy to work out to we've been trying to figure it out for 2,000 years and we still don't know the answer. And that it's so easy to get to a question where we don't know the answer. Now, we could do things like we could say, so let me tell you another thing. The question of the density of prime numbers. That's another question that has been it's been a big question in math. So somebody asked, can I plot the prime numbers? Let me show you a different way to plot that. So let me ask this question. This is a thing which says, how many prime numbers are there less than 100, for example? So this is telling me this is telling me the number of prime numbers less than 100. Okay, so for example, if we say, how many prime numbers are there less than 10? It says there are 4. Let's see if we believe that. Let's just work out the first, let's say, I don't know, 20 prime numbers. Okay, let's see, how many prime numbers are there less than 10? Okay, we can just count them. There are 4 here. And so this is telling us there are 4 prime numbers less than 10. Okay, so let's do the corresponding thing for, let's say, 20. Prime pi of 20. So it says there are 8 prime numbers less than 20. Okay, so let's go figure that out. Yes, it seems to be correct. Okay, so now we can ask this question: how many prime numbers are there less than a particular number? And so let's make a table of those. Oops. And let's plot this. And so what's going to happen here, actually, I'm going to say this just for fun. What's going to happen here is we get this series of steps. Let me do a smaller example. Why do we get a series of steps? Because this is saying less than, how many prime numbers are there less than 3? Okay, there's 1. How many prime numbers are there less than 4? Let's see, I'm reading this off wrong, sorry. I'm reading off the number of prime numbers less than 3 is 2. But the number of prime numbers less than 4 is still 2. So it's just flat there. And the only time when this starts to go up again is when we get to 5, and then we got another prime number, so it goes up again. So it's going to make this kind of stair-step thing. The plot is going to be the stair-step, because it's going to say the number of prime numbers less than 10 is the same as the number of prime numbers less than 9, because we didn't gain a new prime number going from 9 to 10. Make sense? Okay, so we can make, we'll just do this for much bigger numbers, let's say for 200. So this is going to tell us the number of prime numbers less than a particular number, okay? So there's been a lot of math done to try and figure out this function. So if people know fancy math, there's a thing called the Riemann zeta function, which is basically trying to figure out, okay, I'm going to tell you 2 fancy math facts for people who are into that kind of thing. This function is approximately n log n. It's approximately the number times logarithm of the number, and the density of primes. Let's see. I'm saying something slightly wrong there. This function will be basically log n. People have been trying to work out the corrections to that for a long time, and there's a thing called the Riemann hypothesis, which is a complicated math fact about the Riemann zeta function, which all has to do with what exactly is the growth of this function like. And that's a famous unsolved problem in math. These days, there's $1 million bounty for anybody who can solve the Riemann hypothesis and determine basically whether this thing grows more or less like logarithm of n. Okay, so let me show you another math thing. So we've talked about prime numbers, and we've talked a little bit about decomposing numbers into primes. So we might take the number 78, and we could say, so we can ask, what is 78 in terms of primes? Okay, and so that we have a thing we can say factor integer. Okay, this is going to bring together a couple of things we've talked about. So, well, okay, let's start off with 10. So 10 is equal to 2 times 5. Okay, what's 8 equal to? 8 is equal to 2 times 4, but 8 is also could be written as 2 times 2 times 2. Okay, and so the thing I've been talking about so far in telling whether numbers are prime is, can you write a particular number as a multiplication of 2 other numbers? Okay, so one question would be, if you if you're only given prime numbers, if the only numbers that are available to you are prime numbers, can you make every number by just multiplying prime numbers together? Okay, so we could say, for example, let's try and make every number that isn't a prime. Can we make every number that isn't a prime just by multiplying prime numbers together? Okay, so we know 30 is, okay, so 30 would be 6 times 5, but we can decompose that again because we know that 6 is 3 times 2. So 30, again, we can say 30 is equal to 3 times 2 times 5. Okay, so the question is, any number that isn't prime, can we write it as a multiplication of prime numbers? Okay, so okay, so there's a question here, can we visualize this? The answer is yes, but a little bit of code to do that. Well, let me show you. Okay, so the question before us is, can every number be written as, every non-prime number be written as a product, as a multiplication of prime numbers? Okay, this is sometimes called, well, and then the question is, if we can do that, can we do that? Can we do that in several ways? Can we do it in one way for each number, and so on? Okay, so it turns out, fundamental arithmetic fact, which isn't super surprising, we can see why it's true, is every number that isn't a prime can be written as a product of prime numbers, of sufficiently many prime numbers. Okay, so for example, we can ask the question, so I don't know, let's pick a number, let's pick, I don't know, 600, okay? Let's see, how do we write that as a product of prime numbers? Well, it's 6 times 100. Well, 6 would be 3 times 2. 100 would be, I don't know, 20 times 5. Then that 20 is 5 times 4. And let's see whether I learned my arithmetic properly. Is that right? Yeah, that is indeed 600. Okay, so we have a convenient function called factor integer, which will actually take an integer like 600 and it'll tell us how to write it in terms of prime numbers. And what this notation means is it's saying there's 3 copies of the number 2, 1 copy of the number 3, and 2 copies of the number 5. So this is saying it's equal to, oh, I cheated here. That's not a prime number. That's not allowed. It should be that. I've got to write my 4 as 2 times 2. So here, this is saying that 600 is 2 times 2 times 2 times 3 times 5 times 5. Okay? Otherwise, we can say this is 2 to the power 3 times 3 to the power 1 times 5 to the power 2. Okay? So another fundamental math fact, every number that isn't a prime can be written, and actually it can be written uniquely as a product of prime numbers. There's just one way you write it as a product of prime numbers, sometimes called the fundamental theorem of arithmetic. Let's see. So I'm going to, somebody asked, let me see whether I can find for you a, let's look over here. Let's see whether I can find an example of how this, how this works. I think we've probably got one here. Let's see. Let's see, factor tree. Let's see whether that gives us something useful. Yeah, that seems useful. All right, let's see what this looks like. Okay. So this claims to show us how we can break a number down. So this is saying 4 is 2 times 2. Let's pick a number here. Let's type it in. Let's say the number 26. Okay. It's going to show us 26 is 2 times 30. Let me pick a better number. Let's pick the number 600. Let's see whether that works. Oh, that was a bit big. Let's just try the number 100. Okay, so what does this mean? So this is showing us how to break down 100 into prime factors. So it's saying 100 is 20 times 50, and sorry, it's 2 times 50, and 50 is 2 times 25, and 25 is 5 times 5. So we can make this kind of tree, and at the bottom of the tree, we see the prime numbers that make up 100, okay? Let's try doing this for 105, for example. Okay, so this is showing us 105 can be broken down into 3 times 35, and the 35 can be broken down into 5 times 7, and so that's the way that we can break that number down into prime numbers. And for any number we type in here, there will always be a way. I don't know, we type in 230, for example. There's always be a way to break it down into prime numbers. So you can ask questions like, how many prime numbers do we need to use to make a particular number? That can be quite tricky. So for example, we could say, okay, so what, let's see whether we can figure out what numbers, so let's work out, for example, how many distinct numbers we need. So for each number, remember this factor integer thing tells us, so let's do that for 230 here. Factor integer tells us 230 is 1 copy of 2 times 1 copy of 5 times 1 copy of 23, okay? So there are 3 different primes that are involved in the number 230, okay? So one thing we could do here is we could say how many, well, we could ask how many primes are involved in a number, or we could ask, when we do the multiplication at the end, how many numbers do we have to multiply together to get the number we started from? So there is a thing, let's see if I remember my number theory. This is unfortunately kind of, I think, graduate school number theory, but let me just remind myself. Counting multiplicities, okay, yes, this is the right thing. Okay, so this thing, which is called prime omega, is tells us basically the number of numbers we have to multiply together to the number of primes we have to multiply together to get a particular number. So for example, if let's do that for 10. Okay, so that's going to say we need to multiply together 2 primes to get 10. Let's do that for 12. Okay, so let's see why it says that. So let's say factor integer of 12. So that's telling us that 12 is 2 times 2 times 3, just 1 3. Okay, so this quantity, prime omega, is counting the total number of distinct numbers we have to multiply together to get the number we're looking for. So in this particular case, the answer is 3. It's 2 times 2 times 3. So there's 3 numbers that are involved there. So let's try it for a different number. Let's try it for 20. Let's try it. Yeah, let's try it for 100, for example. Okay, so for 100 is 2 times 2 times 5 times 5. So there's 4 different numbers we have to multiply together to get to 100. So let's ask what's prime omega of 100. The answer is 4. Okay, makes sense? Okay, so now let's work out for all the different numbers, let's work out what this prime omega quantity gives us. So let's say the numbers from 1 to 100. How many numbers do we have to be multiplying together to get that number? Out of how many primes do we have to multiply together to get that number? Okay, so first question here, what are the ones here? Okay, so the ones are exactly the prime numbers, because the ones are numbers where the number of primes you have to multiply together to get that number is just 1, because the thing we're doing is just putting in the prime number that comes out. So if we look here, that's okay. So let's line up. Let's make a little table here. Let's line up n and prime omega of n, and let's make a grid of those. Let's put that in a frame. Okay, so this is showing that this is giving us the number and the number of primes we have to multiply together to get that number. So this says 3 is a prime, so we only have to one thing to multiply together. 4 is 2 times 2, so there's 2 numbers to multiply together. 6 is 3 times 2, there's 2 numbers to multiply together. 8 is 2 times 2 times 2, so there's 3 numbers to multiply together. Okay, so there are numbers here, so there are prime numbers where this number of things you have to multiply together is just 1. So let's look here at, let's make a plot here of how many numbers you have to multiply together to get let's do this. Well, okay, no, let's just do this. Let's say, so this is showing how many numbers you have to multiply together, how many primes you have to multiply together to get each number. So the ones that are down here that are the ones, those are the prime numbers. Okay, so now let's try and figure out what are the winners here? What are the numbers that take the most numbers that are the numbers that we multiply the most primes together to get to, okay? So what are the numbers where this prime omega thing is biggest in this picture? Okay, so can we figure out what those numbers are? Anybody got a thought about that? So those numbers, in a sense, those are the least prime. Those are the furthest away from being prime because they're made from. Yeah, it's kind of remarkable. Somebody's commenting on the live stream how random this picture looks. Yeah, this is welcome to the world of numbers. You think numbers are kind of simple, but actually they get pretty complicated. Like that's for the first 1,000 numbers. We do it for the first 10,000 numbers. We're going to get pretty complicated looking. Well, actually, let me show this in a slightly different way for the first 10,000 numbers. Let me go back down here to the first 100 numbers. And let me show 10,000 numbers in a slightly different way. Oops. Okay, so that's kind of the same plot asking, actually, I want to check one thing here. Let me just check that I did this correctly. Let me make sure that it shows. Yeah, okay. So this is showing for the first 10,000 numbers, how many primes you have to multiply together to get each number. It's kind of complicated looking, right? And so the question is, what are the winners here? What are the poke out numbers here? Well, the answer is, let's see if we can figure it out. How do we get to the biggest number by using a so I think what we're going to find is that those numbers are powers of 2. So in fact, what we're going to find is, I think, my prediction, if I know what I'm talking about, which I may not, is that these sort of poke out numbers, the first number that kind of wins against all the other numbers before it, the first number that needs a lot of primes to make it will be the power of 2. So in other words, this number here is 2 to the power 5, which is 32. So why is this true? Well, because the number that's going to need lots of primes, right? It's a number that looks like that, and that will give us 64, for example. The first number that uses, let's see how to say it. The first number that uses, okay, so what's another number that also uses, okay, we're trying to ask, what's the first number that needs 6 primes to make it, okay? The first number that needs 6 primes to make it is going to be the number that has the smallest prime used 6 times, and that's powers of 2. Does that make sense? So for example, the next, we could have another number that needs 6 primes, but it's got a 3 in it, and so it's going to be a bigger number. Right, so let's see. So in a sense, these numbers are sort of the furthest, the ones that need the most primes to make them up. Right, so we could ask the question. So for example, we could ask all kinds of questions here. We could say, what's the average number of primes you need to make a number less than 100? Or we could say, let's ask that question. Let's ask how many numbers. All right, let's do this. Let's say for numbers less than 100, how many of them need how many primes to make them? Okay, so this is saying, let's see, there are, what is this saying? Okay, this is a little confusing because there's a weird special case, which is 1 a prime number? And usually in math, people say 1 isn't a prime number. So this is saying that the number of numbers that need 0 primes to make them is just 1 number, and that number is 1. Okay, so less than 100, the number of numbers that need 25, that need just 1 prime to make them is 25. So actually, we should be able to work out, if we ask how many prime numbers are there less than 100, that better be 25, because those numbers that need just one prime to make them are exactly the prime numbers. Then there are 34 numbers that need two primes to make them, 22 numbers that need 3 primes to make them, and so on. So we can ask the question, if we just say, we can just make a graph out of these, and we could say something like, let's make a histogram, which shows us how many, okay, so this is showing us how many numbers less than 100. This is showing us that 35 numbers less than 100 need 2 primes to make them, et cetera, et cetera, et cetera. Okay, so now we can do the following thing. Let's do this for 1,000. So this is telling us how many numbers need how many primes to make them. And it's still the case that the all-time winner here is that of numbers less than 1,000, the most common number of numbers you have to multiply, the most common number of primes you have to multiply together is 2 primes. Okay, so let's try this up to 10,000. Okay, oh, this is interesting. Okay, so this is actually, let me just do something here to make this work in the correct way. Okay, so it's still the case that up to 10,000, up to the number 10,000, the most common number of numbers that you multiply together to get a number less than 10,000 is 2. Okay, so, but still the 3 is really gaining on that. So in other words, if you want to make a really big number and you want to make it out of primes, what's happening here is that as we get bigger and bigger numbers, they seem to be they seem to not it seems to still be the case here that making numbers out of 2 primes is still the winner. Now, actually, okay, so I think of myself as knowing a fair amount of math. I do not know what this curve is, and I'm not sure. I think this is, so let's take a look. Let's try it. Let's sort of let's try it for 100,000 numbers, and let's see what the result is here. Okay, very, very, very funky. So this is saying, so this is counting the number of prime numbers. Okay, that's the number of numbers less than 100,000 that have only 1 prime needed to make them. This is the number of numbers that need only 2 primes to make them. This is the number of numbers that need 3 primes to make them, and so on. And there are numbers out here in the tail that need 15 primes to make them. Okay, so at the number 100,000, suddenly the most popular thing is to need 3 primes to make the number. In other words, if we look at numbers up to 100,000, the most common number of primes we have to multiply together is 3. This is quite weird, and I actually didn't know this at all. So this is a math fact I didn't know. Let's see whether we can just do one more. Let's try the numbers up to 1 million, and let's see whether it's still what wins for the numbers up to 1 million. And by the way, my guess is that this is a non-trivial math fact to prove if you work out. So for example, we might have the hypothesis that if we look up to numbers that are really, really, really huge, that the average number of primes, so one question would be, if we look for numbers that are as big as you want, infinitely big, will the most popular number of primes keep on increasing as we go to bigger numbers? So still at 1 million, 3 is the winner, and actually, bizarrely, 3 is gaining on its neighbors. Well, it looks like okay. So 3. So let's see whether we can try and figure out. So I don't know the answer to whether, and I think it will be not an easy thing. I think this is a sophisticated math problem to figure out whether the most popular number of primes will be infinitely large if you have an infinitely large prime. Okay, so good. Okay. All right, we've got a suggestion here for making a manipulate out of this. We can certainly do that. Okay, we can just see how this curve changes just interactively. Let's do this here. Let's say m there for the maximum, and let's say m goes from 1 to, let's say, 10,000 in steps of 1. Okay, so this is going to show us, that's really boring there. So this is going to show us, as we increase that maximum, it's going to show us, okay, so still the 2s are winning there. Let's keep going, let's keep going, let's keep going. The 3s are getting, well, let's see what's happening. They're all wiggling around. Let's see here. Oh, we still got the 2s winning here. So we'd have to go to bigger numbers to find out that the 3s were winning. We could compute, we could work out things like we can make a plot of the ratio of the number of numbers that come out of 2 primes versus 3 primes, and we could try and see what that looks like. We can try and guess the answer. Let's see. Okay, let's do. Okay, so now we're venturing into math where I pretty much predict that I'm going to make a claim that I suspect mathematicians have not looked at the thing that I'm about to look at, but we'll maybe they have. Maybe they looked at it 100 years ago. Maybe they looked at it 5 years ago. But let's ask the question: if we look at, let's see how to work this out. We want to know. Well, I was going to work out the number of numbers. Okay, let's see how to do this. Sorry, this is a little bit of a programming thing. To do this efficiently, well, let's say we've got this up to 1,000. What we want to know is, let me see. Oh, I see how to do this. All right, I see how to do this. Let's write a little bit of code here. What I'm going to ask it to do is not the most efficient way to do this, but it will work. Let's see. Take in U that number M, table of that. Let's see, we're going to make, let's see, go up to 10,000 there. And then I'm going to do one thing. Sorry, this is going to look a little weird, but I'm going to say count in that number of 2s divided by count in that the number of 3s. And I'm going to do that. I'm going to apply that to that. And if I know how to program properly, which I may or may not, this should give us that result. Let's see. Okay, so okay, we got some weird stuff at the beginning, but let me make a plot of this. We got weird stuff at the beginning. We could say it's in zeros at the beginning, but let's not worry about that. Let's just go from 2 up here. Let's just go to 1,000 here, and let's get the result. Okay, so we got these weird things because we're dividing by 0 at the beginning, but let's not worry about the dividing by zeros. Let's just work out. Let's just make a plot of this. Okay, so what this is a plot of the popularity of, wow, this is so weird. Okay, this is the popularity of numbers where the number of primes you need to make them is 2 divided by the number of numbers where the number of primes you need to make them is 3. So this is showing, so over here on the x-axis is the maximum number we're looking at. So this is saying up to 600 numbers. For numbers up to 600, this is saying that the ratio of the number of numbers that need 2 primes to make them to the number of numbers that need 3 primes to make them is 1.3. So this is saying that at 600, it's more popular to use 2 primes than 3 primes to work out the number is more often a product of 2 primes than a product of 3 primes. Okay. So this is showing, this is a curve, I've never seen this curve before. And this is a really funky curve that, yeah, okay. Let's try doing this up to 10,000. Okay, it's going to make some complaints there. Okay, here we go. All right, so this is showing us the ratio for numbers up to 10,000. This is showing us what's the winner? Is it 2 or 3? So if this number dips below 1, that means that the 2's lost out to the 3's. And just to live a little bit dangerously, let's try going up to 50,000 here, and let's see whether we can see how long it might take. I'm not doing this computation in the most efficient way. I'm doing it in actually very, very kind of dumb way. But this is going to try and work out that curve for 50,000 numbers. Come on, come on, come on. I'm doing it in a really dumbly inefficient way. But so, you know, the thing to realize when we see a curve like this, it is really remarkable that from something as simple as asking about prime numbers and arithmetic and so on, we get out these really complicated curves like this. And this is, in a sense, this is why math is hard. That, you know, to predict, you know, will we ever have, will this ever go below 1? Will it ever, if it keeps going for longer and longer and longer, will it eventually have a start going up again? Will it not start going up again? Those are really hard things to figure out. And why is this taking so unbelievably long? So somebody, okay, somebody's sophisticated here. Write me some proper, oh, here we go. We got this one. Ah, there we go. Okay, so this one, so by 50,000, we're seeing that the 2's are losing out. We got down to 0.95 here. That means the 3's are more common than the 2's to this point. Okay, so this is so it's kind of interesting to see. You know, again, we've gotten to math that's really okay. So there's all kinds of questions here. Simon is asking on our live stream: is a number more likely to have an odd number of primes or an even number of primes? That's a really good question. Go figure it out. Bet nobody knows the answer. So we can also do, this is one particular way of counting how many primes are in a number. We can also ask things like how many distinct primes. That is, when we say a number is 2 times 2 times 3, we can say we're only counting the 2 and the 3. We're not saying we're not counting how many times the 2 gets used. Look, when we're talking about primes and numbers and things, I think there's one more fact that you guys should know, which is about this operation of factoring numbers. So, you know, when we multiply two numbers together, okay, fine, we multiply them together, we get the answer. It's pretty easy to multiply those numbers together. And you probably, oh gosh, I probably with great effort could do the long multiplication to figure out what those numbers multiplied together is. I don't think I've done long multiplication. I must admit, I don't think I've done long multiplication by hand as a human in longer than you guys, than the younger ones of you guys have been around. I use a computer to do it all the time. But the question is, how about going the other way? How about going from this number to work out what its factors are? How about making the prime factorization of a number? Okay, so there's an interesting fact that if we take two numbers and we multiply them together, okay, we've got these numbers. It's pretty easy for a person, a computer, whatever, to multiply those numbers together. But it turns out it's much harder to figure out what the factors of a number are. And one way we could figure out, what's a way we could figure out what the factors of a number are? One way we could do it is, let's say we just have a table of primes. We could just say, does this prime go into this number? Does this prime go into this number? And so on. So let's take this number here, and let's say we can just work that out. We can say, let's make a table of primes, and let's make a table of the first, I don't know, 100 primes. And then we could just ask for this number here. So one way we could do it is just take that number and divide it by all of those primes. Okay, so to say that the number, so what this is going to ask is, whenever this is a whole number, it says that that prime goes into that number. So in other words, that number is divisible by that prime. Okay, so what we're seeing here is a few of those primes that number is divisible by. Most of the time it isn't. But so one thing we could do to find out if a number, to find out what a number, we can also just ask, we can use some, what is it? We could just say, for example, let's say, is this divisible by 3? Okay, it is divisible by 3. So because that divided by 3 is a whole number. So that's also saying that that number there, if we multiply it by 3, that's part of the factorization of that number. but now in order to get the full factorization of that number, we have to break this number down again into primes. Yeah, this is a good way to do this. We're saying what numbers out of, okay, that's just saying which numbers less than the 100th prime go into this number that we picked here. Okay, so one way to find out what the factors of a number are is just to try all the possible primes. Okay, now, clearly a number, okay, this is another little math fact. So what's the biggest prime you have to try if you want to figure out whether the number, I don't know, 5 million is prime? Obviously 5 million isn't prime because it's an even number, but 5,000,001 might be a prime number. Or we want to figure out the factors of that number. What's the biggest number you have to divide it by? That's the biggest number you'd ever have to try dividing it by. Well, the biggest number you'd have to divide it by is a number such that that number times that number is this. And so, a mathy thing, the biggest number you'd ever have to use is the square root of that number. So if we try dividing it by primes up to 2236, then that's as many primes as we need to try dividing it by. We clearly don't need to try dividing it by a prime that's bigger than the number itself, because the number clearly can't be a product of primes that are bigger than itself. But the biggest numbers that it could be products of, the biggest way that it could be made up of primes is to say that it is a particular prime multiplied by that prime. Okay, so that kind of limits how many primes we have to test to figure out if this number, to figure out what the factors of this number are. Okay, so kind of another question is there, so one way to work out the factors of a number is just try dividing it by each possible prime to see what prime goes into the number. Problem with that is there's a lot of, that means you have to divide the number by as many primes as there are up to that number. And that, as the number gets bigger, we saw before, the number of primes gets progressively much bigger. And actually, that approach, the number of division operations that you have to do will go up. It'll be, well, we could work out how many it is, because in fact, the number of division operations that we have to do is exactly, wherever it was, this function here. It's the number of primes, well, it's the number of primes less than the square root of the number. So it goes up like this. And that, so in other words, as we're trying to work out whether the factors of the number, it will have to do this many divisions. And this is not as big as the number itself. It's actually roughly divides by the logarithm of the number, but it's roughly proportional to the number itself. So if you compare that with when you do, okay, so imagine that you're multiplying numbers together. Let's go back down to the bottom here. Imagine that you're multiplying, some number here, 234 times 567. Question is, how many multiplications do you have to do to work the answer out? Well, the answer is you have to multiply each digit with each other digit. You'll end up having to do a number of multiplications that is actually the number of digits in this first number multiplied by the number of digits in that second number. But that's a much smaller number than something proportional to the number itself. Anyway, what I'm trying to explain is to multiply numbers together is really quite simple. To factor numbers, to break them apart, is quite hard. And so this is an example of a type of problem where to do the computation in one direction by multiplying numbers is easy, but to do the computation in the other direction, breaking a number apart into primes, is really hard. And so this is a question people have tried to figure out for a long time: is there in fact an easy way to break numbers apart into primes, or is it fundamentally hard to break numbers apart into primes? Is it something where you need to use you need to essentially do something that's almost equivalent to trying to divide by every prime. And so there's a fancy name for that in theory of computing, which is the P equals NP problem. The multiplying numbers together is a problem that's said to be polynomial time, because it's the amount of time it takes is just the square of the number of digits in the numbers, roughly, or something smaller than that. Whereas, well, this is a little bit complicated. Let me not go into this. If people are interested, I can tell you how that works. But the basic point is, so far as we know, there's no way to factor numbers that takes only about as much effort as it takes to multiply numbers together. And so you might say, why do we care? Well, actually, many of the codes that are used to make computers secure, the codes that are used to do things with passwords and digital signatures and all those kinds of things, they're all based on this fact that it's much harder to break a number apart into factors than it is to multiply numbers together. And so, for example, one typical example of that, a thing called public key cryptography, basically what happens is you make a number out of primes. So we take a big prime number. So let me take a random prime of size. This number is a prime number. It's just I randomly picked it. Let's pick another random prime number. Okay, so there's two random prime numbers. Okay, so now I can multiply these two random prime numbers together. Okay, and and that's the result. And the thing is that what I can do is I can keep privately what these individual prime numbers are, but I can tell people publicly what the product of these prime numbers is. And by doing a little bit of number trickery, which I could show you, there are things where people can, where you can kind of, you can check that I must have these prime numbers kept privately, but all I'm actually showing you is these prime numbers multiplied together. And the fact that I can kind of prove to you that I have them privately without showing them to you is something that is a result of this fact that multiplying numbers together is much easier than breaking numbers apart and factoring them. So that's so one of the things that people are excited about these days is, could quantum computers factor numbers as fast as you multiply numbers together? I personally think the answer is no, but many people think the answer is yes. That's a complicated physics story to address that. But this question of whether it's possible to break numbers apart as easily as you multiply them together, nobody knows the answer to that. That's actually another problem that I mentioned, the Riemann hypothesis, which is a problem on which there's a kind of $1 million bounty for figuring it out. There's a $1 million bounty for figuring out this question as well, or the general version of this question. Let me just tell you one more fact like this, which is a surprising fact. It is to know whether to break a number apart into factors is really difficult. Nobody knows how to do it efficiently. You might think that would mean that to figure out whether a number is prime is something that's really difficult, and you couldn't do that without essentially trying to divide the number by all numbers smaller than it or something. Turns out that's a case where only a few years ago, people figured out an algorithm that allows you to work out whether a number is prime comparatively quickly, much more quickly than just by dividing by numbers. So it's so when we ask, is this number prime? So I'm pretty sure we're going to be able to figure out, even though, sorry. Okay, so if I give it this number and I say, and I ask it to factor that number, I'm pretty sure my computer is not going to be able to do that. Let me just give it that number there. I'm pretty sure it's going to sit there waiting for a long time. Oh, it proves me wrong. That's so disappointing. Okay, so it was a little bit more efficient than I expected. If I make this number sufficiently long, it's just going to sit there and sit there and sit there, trying to figure out whether that number is what the factors of that number are. Ah, I managed to get it in that case. Okay, two very long primes there, multiplied by some smaller numbers here. But I bet if I ask it, is that number prime? Let's see whether it's going to prove me wrong here. Oh, okay, boom, immediately says it's false. It isn't prime. So there's it's possible to figure out the numbers. It's possible to figure out whether a number is prime quickly, but it isn't possible to factor it quickly. So someone is asking how long are the numbers that are actually used in public key cryptography. Let's just do that for a second. Let's see what I can look up here. I want to let's say, so when I do this is fancy public key cryptography. This is these are the private key of public key cryptography is basically related to a prime number, and the public key is related to this product of numbers. And what this is saying, I guess, is that the how do I read this? This is I think this is saying that this is a 2000-bit prime number. Yeah, that's right. So the number that's being used is a number that has 2000 bits, which is otherwise known as what is that? That is a number, well, we can just work it out. 2000 bits is a number, okay, so that's the sort of rough size of the number that would be being used as a key for public key cryptography. So that's how many digits are in that number. We can work that out. That has 616 decimal digits. And so this is so we're generating what's happening here is yes, so this is I'm having a little bit of a hard time remembering exactly how this works. One of these things is going to be the way it works with the prime numbers for public key cryptography. There are a couple of different methods, and they use they use another math fact. Okay, they use a math fact that they use an interesting math fact that if you look at the remainder, when you divide the power of a number, let's see, I have to translate this a little bit. It uses the well, I have to think about this a little bit more, but this gives you a rough sense of the size of the numbers that are used as keys in public key cryptography. And the question of how long a number you need to use depends on kind of how fast computers are. And the idea is to use numbers which are long enough that no computer we could seriously imagine building would ever be able to factor that number. All right, we should probably wrap up soon here. But maybe if there are some questions, I'd be happy to try and about this this kind of math. And I'd really like to know whether people were able to follow this, whether this was interesting. I mean, I can. Okay, there's a question here about. I mean, there are lots of things we can do with prime numbers. There's a whole area of math called number theory, which is about doing things with numbers. And sort of one of the most popular topics in number theory is prime numbers. It's I mean, there are just so many different kinds of things we can do. So you know, we talked about breaking numbers down as things where we're multiplying numbers. We can also ask about things like how do we break a number down, adding it up? That's another kind of thing we can do. How do we make 10 out of adding it? What are the different ways to make 10 out of adding it together? That's another interesting math problem. Like, how many different ways are there to break 10 down into an addition of numbers? How many, lots of different kinds of things. What I think is really interesting, so a couple of things to sort of takeaways from this. One is, it's really fun to try doing experiments in math with a computer. Everything that I did here, I'll post this notebook that I used, and you can use the free version of the Wolfram Cloud, for example, to do everything I was doing here today. Don't try running too long integer factorizations, or it'll burn our cloud computing resources like crazy. But you can try any of these things. Try doing experiments with, try doing some of these experiments with primes. If you find interesting results, send me mail. I'd be interested to know. And it's a lot of these things where one is doing experiments with a computer with numbers. Don't assume that these experiments have all been done before, because people haven't had computers that can make it easy to do these experiments until quite recently. And so they may very well not have done these kinds of experiments. Look, the other takeaway from this would be this thing that the math you learn in school is you don't run into these kinds of things. You won't see in kind of school math, when you talk about prime numbers, you won't see a curve that looks like that. Nobody's going to show you a curve that looks like that typically. Because what happens is that there's math that is easy for people to do. It's pretty hard for a person to make this curve. It'd take you a long time to work this out. There's math that's easy for people to do, and that's what you can learn to do, and you can learn to do it in school, and you can learn to do calculations with it. There's different kinds of math that computers can do, and one of the things that a lot of the math that we make use of in everyday life is math that's quite easy to do. Like, if you say, you're doing simple math with, I don't know, with financial math or something, most of that math is quite simple to do, because we've set things up so that the math we need to use to do financial calculations is math that's quite simple. But if you just go out and say, let's ask questions about math, like questions about numbers, we can ask all kinds of questions which aren't necessarily easy to do. And so one of the things that they don't typically teach you in math is it's actually pretty easy to go kind of off the rails with math. That is, to go and do things where you think it's an easy question, but actually it turns out it's really hard to work out the answer. Because most of the math that you'll do in school is math where we know it's pretty easy to work out the answer. But you can still ask simple questions and end up finding out that the answer is not simple. Even though the question is simple to state in terms of math, it's hard to work out the answer, and the answer can be really complicated. And so it's an interesting fact about math. It's a very fundamental fact about math. It's kind of the reason that math has been, when I talk about things that people started doing, 2,000 years ago, and we still don't know the answer and so on, that's why things like that are happening. That the questions were quite easy to state. There are questions that people could ask 2,000 years ago in terms of math, but we still don't know the answer even now. That's a consequence of this fact that math has this feature that you can, even though it's simple to ask the question, it can be really hard to answer the question. All right, well, I think that's it for now. And if people think this was interesting, maybe I'll try and do another one of these, maybe about a different topic like geometry, or I could also talk some more about different kinds of things with numbers. Thanks for coming, and hope you learned some things. So thanks a lot, and I'll sign off here.